Hello YouTube and welcome. In this video, we are going to be creating an infinite reverb, which is perfect for lush ambience like this. And since we are going to build this reverb from scratch, we're not only going to better understand the theory behind reverb, which can make us better audio engineers and producers, but we're also going to be able to hack it and create a new effect like this. So before we build the reverb, we have to understand how it works. That only makes sense, right? So today, let's talk about how algorithmic reverb works. And what I mean by algorithmic reverb is it's a type of reverb that is going to be lightweight and efficient compared to something computation heavy like convolution reverb or ray tracing reverb. Algorithmic reverb, but think simple, think lightweight. So let's try and create a really lightweight model of acoustics. Let me introduce you to my friends Bob and Alice, and they're going to explain acoustics to us. And let's say Bob and Alice are standing in a park, and they're super tall. They're much taller than this tree. And Bob wants to talk to Alice, so he's going to say, "Hi, Alice." And the sound is going to travel towards Alice, right? And let's say that it takes T1 seconds to get to Alice. And, you could figure out what that time is if you knew how far they were standing apart, and we know the speed of sound. But sound doesn't travel in a direct path like a laser beam, right? It's going to spread out. So another path is going to go downwards, and it's going to reflect off the ground, and it's going to go back to Alice. We can say that this takes T2 seconds to get there. So that's about as basic a description of acoustics as we can get. What if we tried implementing this in an effect rack? So we'd have our input signal here. It goes first into a delay with time T1, and that just goes right to our output. There's Alice. And then we're going to tap in on the input and model the second path with time T2. So T2 is always going to be longer than T1, remember? It's just the way it works. And then we can also make this a little more accurate, like this bounced off the ground, right? This is going to have some attenuation. And then this will tie into our output. So there we have it, and you might recognize this. That's a comb filter right there. And if you've been following my series on physical modeling, comb filters show up all over the place. Like, it just seems like they're close at heart with physical models. All right, so is that all the theory we need? Well, no, a comb filter doesn't actually sound like a good reverb. We need to go a little bit deeper with our model. But we have to start somewhere, right? So the next thing I want to talk about is Schroeder reverbs. So how these would work is that we would have a whole bunch of comb filters. So what we drew above, that was a model of a single comb filter, and then Schroeder's like, let's have a bunch of these. And it kind of makes sense, right? Like there's really like many paths that could reach Alice. So it kind of makes sense that if we just took a bunch of comb filters, maybe this will sound like acoustics. And, I think he used more than 3, but we'll just do 3 for now. And then these would go into a bunch of all-pass filters. So combs, and he'd have, let's just say, ×4 of these all-pass filters, and that was his output. Okay, so as I mentioned, the Schroeder reverb actually kind of sucks. But that's okay. It's actually good to learn about because it's not going to be so far off from our final design that doesn't suck. And so this is where I want to introduce FDNs. And this is where we're going to add the concepts of feedback, or we're going to make feedback a more important part of the design, and we're going to add coupling. And the reason I say feedback is more important here is that this all-pass filter technically has feedback in it. So go look up how Schroeder all-passes work if you want to learn more about that. But that's how the Schroeder reverb was able to get like some longer tail in its reverb, is that these all-passes have some feedback path inside of them. But the FDN is going to add this in a much more important way. So this kind of makes sense. Let's revisit our model again so we can tie this back into how real acoustics work. Let's say Bob is in here and he's in a room, and there's kind of like all these different delay paths that could happen in a room. Like for example, that's like one of you'd say that's a mode of your room, and that's a mode of your room. And when Bob talks, you know, sound's going to go out everywhere. So some of the sound is going to go over and it's going to scatter, and it will excite this room mode right here. But some of it's going to reflect. And then right here, some of it will keep reflecting. But some of it's right here is going to, you know, scatter. It's going to go back with this path, and it gets complicated really quickly. I can't draw exactly what happens without just scribbling all over this page. But I think the main point is that there's these different modes in the room, and they don't just kind of like feedback with themselves. They couple to each other. So that's kind of what the Schroeder is missing, is that the Schroeder would be like if you just had this mode here bouncing back and forth, and you just had this mode bouncing back and forth. With the feedback delay network, we are going to have this mode bouncing back and forth, but it's also going to kind of couple with this thing, which also kind of couples with this thing. And so that's how we're going to make it more realistic. So how do we do that? Let's go to our next system diagram. So this type of system is going to have its input go into, I bet you can't guess, it's going to be another delay. And it's a delay network, right? It's an FDN. So we're also going to have at least 2 delays, and we could have as many as we want, up to like delay 5,000. But for this example, let's keep it simple so we can understand it clearly. And the outputs of these are going to be simple. We're just going to have a summing option that is going to put the output of our 2 delays. It's essentially 2 delays in parallel, right? That's what I should say. The feedback path, though, is where this gets potentially a little complicated, but it's not too bad, I promise. So we're going to tie in to both of our delay outputs. We're going to put them into what is called a feedback matrix. And this feedback matrix, I hope it does not intimidate you, because I promise it is not that complicated. Like if you are familiar with mixing audio signals, mixing multi-channel audio signals, you know, we have 2 inputs and 2 outputs. And this is basically the mixing console, basically, that determines the volume adjustments that we make. So we have in 1, in 2, out 1, out 2. And traditionally, like in math, we write matrices in brackets and we have all these numbers like 1, 7, 5, 3. But all those numbers mean is that in our little, in our black box, which is kind of like a mixing console, we have some connection from the first input to the first output. And there's some, you know, gain inside of it, like G11, like it changes the volume. And that's what this first number means. We multiply our input 1 by this G11, and that's connected to our first output. But the first input has another connection, which goes across to the second output. And that is in our matrix G21. 1. So it's called 2 1 because it's to the second output from the first one. And then we have yet another connection inside that goes from the first, or sorry, this goes from the second input to the first output. And that is going to be over here. This is G1, 2. And lastly, we'll have the final possible connection, which is the second input to the second output, and that's G2, 2. And so, you know, it's really not that complicated. It's just 2 inputs, 2 outputs, multiplying them by different values. And then, of course, you know, the outputs sum together these 2 different connections. And that's what gets fed back into our delay lines, respectively. And just this matrix notation down here, this is really just because it ends up being simpler once we have really big, like once we have like 16 delays. You know, we don't want to draw all these arrows. They're just going to go on top of each other when we have 16 of them. So this matrix is going to be a lot more efficient of a way for us to communicate how are we adjusting the volume. And the reason these are all connected together is because, like I said, these feedbacks are coupled. So we have, like in this example, we have T1 talking to T2. We have T2 talking to T1, right? There's crosstalk between these. We also have delay 1 talking to itself. We have delay 2 talking to itself. And this matrix over here defines like how much everything is talking to each other. It's basically the god of this FDN system. It defines everything. So now that we understand that, we can go build this. All right, so let's jump over to Ableton, where I have this marimba sample pulled up. And that's just because I think that would sound really cool with a lush reverb on it. And then we can pull in this max audio effect. And if you have the full version of Ableton, you should be able to play with max, which is cool. I'm going to click on this box here to open up the max editor. All right, first things first, I am actually just going to delete all this stuff that we don't need. And let's just grab this plugin. And the first thing I'm going to grab is mc.dupe. And this is going to duplicate our plugin input. And we can say this should duplicate it like, let's start with a 4-channel delay. So this means we're going to have 4 parallel delays. And then I'm going to grab mc.mixdown, which is going to sum these signals back down. And I'm going to choose auto gain. I'm going to enable that so that, you know, we're not going to be 4 times louder. And we're just going to test that this works. And then I'm going to choose mc.plug out. And when I connect these together, what I'm hoping is that this is going to give us just our same audio. Cool, so that's working. Okay, so we can just go ahead and add the delay next by typing mc.delay. And then we want an argument of, we can say like 96,000, which will just give us a maximum of 2 seconds delay. And then we're going to type @chans4. And that's going to give us 4 delays inside this. So the reason I'm doing the mc.delay is because you can pack multiple different delays with different delay times in this object, which is really cool. It's going to end up being cleaner. I did have to pay extra on top of the actual like Ableton Live Suite version of Max that come with this. I had to pay extra to get this. And I honestly did it just for this video because, well, at first I was thinking maybe I'll use the free delay, and that's good because if any of you out there didn't pay the full version, you can follow along and do it for free. But, you know, these 4 delays packed into this one thing, it's a lot cleaner to do it this way. And I thought it'd be better. It'd be easier for everyone, even those of you that don't have the MC version. It's still easier for you to watch me make this patch in a clean way where we have fewer objects going on. It's simpler to read. it's even easier for you. Even if you don't have the full MC version, you can figure out from this video how you can build this with, you know, non-multi-channel delays. But in this video, let's do it the clean way. So I'm gonna next type in mc.sig, and this is going to give us 4 different delay times. So mc.sig, I'm gonna do chans4, and we're gonna connect that to this delay time input, and then we need to send a message to this signal to tell it to send, I want basically random delay times right now. I don't want to think about what's a good delay time till later. So right now I'm going to type deviate, which is going to give us random delay times with a standard deviation of, let's say like 2,500, and it's going to be centered around 10,000. So like on average, these 10 delays should have 10,000 samples of delay. So now if I play my MIDI, that's what it sounds like. Okay, next, let's get the basic regular feedback working first, and then we can add the feedback matrix next, just to take this in baby steps. So the first thing we need is this mc.tapin and tap out, and I'll do an argument of 1 millisecond to each of those. And tap in, tap out, it's basically like another delay. I couldn't get this working with just tap in, so that's why I'm using both delay and tap in. But basically the problem is tap in, tap out. I couldn't get the multiple delays in one object working with different delay times. And the problem with this MC delay is it doesn't let you feed back. So this tap in, tap out is somehow needed to get the feedback signal to work. And then something else we'll want in the feedback path is we'll want to multiply this. We're going to type in mc.star, and we can put a default in. This is probably a good chance to add a dial, because we'll probably want to control the amount of feedback, right? So let's add a live.dial. Okay. So now when we, actually I don't want this connected right here. This is only going to be in the feedback path that we attenuate. So we can maybe put this to the side. Right out of tap out, we're going to connect to our output. And then after this feedback, like multiplication scalar thing, that's where we're going to feed back into the delay like this. So let's see what that sounds like. Hopefully we don't blow our ears off. Next thing I want to do is clean this up a little bit, just because all this tap in, tap out stuff, it's really not that useful to look at when we're reading it. So I'm going to select all these objects, then you press Control-Shift-E, at least on Windows, and that can wrap these all up so we don't have to look at all those objects when it's just doing one thing. Let's give ourselves some more room, and then since these feedback paths kind of cross paths with like the main output, it gets a little confusing. So let's change their color. I'm going to select both of those, then go to Object, Color, Pink. And now it's kind of more clear. This pink path is our feedback path. Let's maybe add some other controls I want in. So any reverb plugin should have dry wet. So I'm going to type bpatcher, and then I'm going to do mc.mix, which is actually a custom object I made. Well, I mean, I'll have this patch for free, so you can grab it. Otherwise, you basically need to mix one channel with the other, not too hard to implement yourself. And over here, mc.pack, or rather, I'm going to pack the stereo input into one multi-channel signal. And I'm going to send that to the left input of this mix knob, and then I'm going to send the output of our reverb over here to the second input, and then we're going to send the output of this mix knob over here. So now I should be able to control, this is mix turned all the way down, and now when I turn it to the right, it's all the way to reverb. And when we go to the middle, we get some dry, some wet. And by the way, I know this isn't really reverb yet. Don't worry, we're gonna make this better. Another control we'll want is MC.1pole. I want to add dampness to this, so let's have another live.dial. And then where I want this low pass filter is between the feedback path and the delay, but I'll also essentially want the input to go there too. So let's put our input into this low pass filter. And then let's also put our feedback into the low pass filter. All right, with that housekeeping out of the way, we're finally ready to add our feedback matrix, which is gonna make this a more legit reverb style plugin. So I'm gonna type P to create a custom subpatcher, and then I'm gonna type feedback 4x4, because that's what we want to implement is our 4x4 feedback matrix. I'm gonna make this big. And the values for our matrix, I'm going to pull up really quick. These are them right here. So basically, I want along the diagonal of this matrix it to be equal to 1, and everywhere else it's going to be equal to -1, and we don't want to forget to, at the end, multiply it by 1/2. So I need 4 inputs, evenly spaced, and then I'm going to start adding this matrix. So it's going to be 1 along the diagonal of this matrix. So I'm going to type star tilde, or multiply, and then 1 dot. So it's going to be 1 in that first part, and then for our second part of our matrix, it's going to be -1, and then we're going to have another -1, and yet another -1, and then I'm going to copy this whole row and put it down 1. And then basically I just need to switch these two values. So that now this first one is -1. And remember, I'm just following that reference again, just typing in all the values right here. So -1, now this second one now becomes +1. The rest can stay the same. Once again, I just need to swap these ones. Now this second one is negative. This third one is positive. And one more time, copied, that one needs to be negative, and our fourth one is positive. So basically, these 4 should be multiplying by +1, and the rest should all be multiplying by -1. Okay, so these are all of our matrix values. Next thing we want to do is connect our inputs and our outputs. So first let's create our outputs, and I'm going to do something kind of maybe not the most standard thing. So I'm going to have the outputs on the right instead of on the bottom. It's going to make our routing a little cleaner. And now here's going to be our strategy of connecting our inputs and our outputs. For the each input, it's going to connect to everything on its column. And then each row here is going to connect to each row of our output. So for example, on 1, we're going to go connect up this entire column to 1. This is the 1 column baby. And as I go along, make sure I keep things nice and tidy. And then each row is going to connect to its associated output. So I can go through here. I'm clicking Control-Shift-Y, by the way, which is what makes these routed a little cleaner. And then I'm going to select all of them and give all of our inputs, or sorry, all of our wires coming from our first input the same color. It'll help us keep track of it. So let's give these all a nice pink color. Then we're going to just repeat this process on the second input. So these next ones, repeat the process. And then this last one, same thing. Okay, so we can minimize that window, and now that's everything that's inside of this little nice packaged 4x4 matrix, and we can now package this up a little more. I'm going to do MC dot unpack pack 4. And what that's going to do is we're going to take this feedback path and put it into here. We're going to split that out into the 4 different delay lines because we need individual control of them at this point. And then, you know, this matrix multiply is going to do our feedback matrix. And then we are going to do the opposite. We're going to do MC.pack. And we're just going to load all of these, this feedback matrix back into a multi-channel input. And we can pass that back to our feedback. So now let's hear what that sounds like. Okay, so there's one thing I forgot to do, and it's important. You might forget to do it too. This matrix needs to get multiplied by 1/2. And by the way, what this matrix is, I'm looking at this reference. This reference is awesome, by the way. I'll link it in the description. This is basically the Bible for physical modeling synthesis. And this section is on reverb sections, and this is a type of feedback matrix which is lossless. So this is how we're going to get infinite reverbs. But one thing we got to keep in mind is this feedback matrix has a scaling factor of 1/2. So at 1/2 is the point where it's going to be lossless. That's where we're going to have infinite reverb. So I got to just go over here. I just got to type MC dot, multiply. That's the star symbol. And we're going to multiply by 0.5. And I know we already have a multiply down here. This is packaged up this way because we want to make this whole little section over here complete as the feedback matrix so we can package it up later. So now that we've done this, now we should be able to get infinite feedback by setting this up to 1. Yeah, we're already in good shape. I would like to package this up. Again, I'm going to click Control-Shift-E, and we're going to call this a multi-channel feedback 4x4. All right, so where do we go from here? Well, the first thing we could do is we could increase the number of delays. Like I started with just 4 to make it simpler while we're getting started. But if we wanted to make this a less cheap reverb, we could just increase the number of delays. But maybe before we do that, let's have some fun and start hacking this reverb. So I think a fun thing we could do to hack this is, since we built this from scratch, we can actually play with this feedback path. And you can actually drop third-party plugins into here. So for example, like I'm trying to think of something really weird, like frequency shifting. Like what would that do in the feedback path? So I'll need to unpack this multi-channel signal. So I'm going to type mc.unpack. And I think I need to say 4. So it unpacks to 4 channels. And then I'm going to put the first 2 channels to this frequency shifter. I guess we'll need a second frequency shifter. Maybe I'll only connect this first one, and then our 4th one we can leave dry. And then we're going to do mc.pack to put this back in with the rest of our friends. And we're going to put our frequency shifter output here. And then our 4th channel we're just going to pass right through. And now when we replace this back to where it belongs, we can start messing with frequency shifting with this infinite reverb. See what that sounds like. Pretty wild. And let's try out this weird frequency shifted reverb hack with some different samples. Like this one sounded pretty cool. Yeah, you could get some really weird sci-fi stuff going on here. Honestly, I kind of just want to keep playing with this. And let's see, where did those frequency shifters go? Here they are. Let's try playing with these some more. So it's when these frequency shifters are in opposite directions that's pretty cool, just because all these feedback paths couple to each other. I think that these frequency shifters are now coupled to each other as well. And so you've got one trying to push the frequency up, one trying to push the frequency down. And it's really kind of pulling it in different directions, and it sounds so weird. Let's see what that does. All right, to wrap things up, let's make a more powerful reverb by increasing the delays from 4 to 16. And once again, I'm going back over to my reference. This is that textbook on physical modeling synthesis, and they talk about how this is the first thing we implemented, 4x4 matrix. Now we want to go to 16.1, and the nice thing about this is there's a recursive definition, so we don't have to go down to the the ones and minus ones anymore. We can just use our matrix, and if we have 16 copies of our matrix, we can make this a 16 matrix. So we're gonna want to create a new patcher. So I'm going to click on this. I'm going to press Control E. And then when I open this up, this feedback matrix is inside. And what I want to do, I guess we're going to want to copy this reference. So we're going to want to have some of the, notice that some of these have minus signs. So in some of them, we have to multiply everything by -1 again, like invert the sign of the matrix. But it's kind of the same thing. We're across the diagonal, we'll want just the regular matrix, and then everything else will want a minus sign. So what I'm going to do over here is, well, first off, let's create 4 inputs and outputs. And then we need to have 4 diagonal matrices, which are going to be like this. And these are, the reason I'm building it this way is just because everything else is going to be have to be inverted. So we'll want something like this. And then the other ones we're going to need to put a minus sign in. So I'm going to double click on this, and then we can just put the minus sign right here. So instead of multiplying by 0.5 at the end, we can just multiply by -0.5. And that's going to make this, I can rename this. This is going to be an inverted matrix. Well, it's not inverted. That's the wrong word. But it's like negative matrix. And then we're going to copy this basically to all the other parts of our 4x4 grid. So we can take these two, copy them here. Okay, so now the idea is that these four are just copies of our original matrix that we were using, our original feedback matrix. And these ones are the same thing, except they have that negative sign added, which I talked about, and same as these down here. So once again, it's only along this diagonal that we keep the extras. Everything else has a minus sign. And now we're going to go through the same process as before. We're going to connect here, connect here, connect here. And then these all connect to the different outputs. And then I'm going to make them routed a little bit cleaner. And we're going to give them a color for everything that comes from input 1, just to keep track. Same thing for channel 2. Same thing on this third column. And our last column. Once again, columns are all connected together and rows are all connected together. And along the diagonal, you have your regular matrix, which we already built, that looks like this. And it's a recursive thing, so they should all look kind of symmetrical to each other. And I guess that's all I have to say about that. Now, I kind of built this in a weird way, so let me fix this. What we really want here is this is a feedback 16 by 16, and we need to unpack this into it. And in fact, it's not completely unpacked because those should all be multi-channel signals. So what we really want is mc.separate. And we want to separate out 4 channels, 4 channels, 4 channels, and then I can leave the last one blank because this will just have everything that's left, if that makes sense. So yeah, now we have 4 channels going to this first input, 4 channels there, 4 channels here, 4 channels there. And now is when I'll want to change everything over here to be 16. But now, yeah, now we have 16 channels coming in and 4 channels, 4 channels, 4 channels, 4 channels going into this, which is good. Because if you remember, we built all of these expecting 4 channels. So that's exactly what we want. And now we can do mc.combine. And this is going to then combine these all back into a 16 channel. Oh, and I need to give it, we're going to say we're going to combine 4 different inputs. Now coming out of this, we have 4 channels, 4 channels, 4 channels, 4 channels. And then when we put this back into our attenuation path, that would be the right number of channels. But something we have to remember, let's check our reference. Let's not make the mistake I did last time. We need to multiply this by half. So we're going to do 0.5. And this is different than the feedback. This is just actually in the definition of the lossless feedback matrix. We need an extra half out here. So now this can go in there and we'll see if this works. It sure doesn't, and I'll bet you I know why. I think it's because we need to send new delay channels in. So I do need to think of a cleaner way. If any of you guys knows Max better than me, please let me know in the comments what's a better way. You have to click on this message again to get new delay times There you go. That's sounding better. So there you have it. Now I've showed you how to scale up to 16. You could actually follow the same process. It's a recursive process. So you could do the same thing I just did, but to scale this up to whatever's the next one, I guess, think about it. But you can make more delays by following the same process we did. And then you can have even more delays. But I think, honestly, I've heard that 16 delays is usually enough. From here, where you want to make things better is you actually want to not just randomly assign the delay times. You want to be more specific about which delay times you're using. There's some better practices to use than this random process I did. That could be for future work. I think what we've done today is already pretty cool, especially the part where we hacked this and put frequency shifters in the middle. That was pretty sick, I have to say. So yeah, I guess this is all I have for today. I hope you learned a lot. I've been working on this for a couple weeks, so it definitely took a lot of reading of this textbook I was telling you about. I'll give a link in the description. I hope I was able to distill the knowledge I was learning from that textbook into this video, and I hope you're able to get something useful from it. If you did, it'd be really helpful if you could give this video a like and subscribe. Always helps grow the channel, share with more people. Anyway, that's all I got for you today. I'll see you next time.